Thank you, Martin, and thank you, everyone. And it's true that I have two hats, but today I'm going to be wearing one, which is a PML one, as not so much scientific director of the lab, but as a scientist. For some time, we've been, you won't see this slide so much, but hopefully the others you will. For some time in the last 3 years, we've been working with a number of institutions in the UK, from PML, NOC, University of Sheffield, CFAS, IRD, the University of Plymouth and Portsmouth, and WorldFish, in trying to develop a system to predict potential fish production worldwide and the socioeconomic consequences of any changes as a result of climate change. And I'm going to show some of these slides of the results of this program, but in terms of introducing, in a way, the debate later today, I'm going to just use my last 3 or 4 slides to just bring a few issues to the table. This program was called Quest Fish. You can see that. And the main objective of it is trying to move from having global climate models, if you can see the red line, I'll move slowly, global climate models that define the world in a changed climate, downscale to regional physical biological shelf sea models, and I'll describe in a moment what that means, and from that estimate a potential for fish production worldwide, and then get to the socioeconomic consequences. The reason why we needed regional physical biological shelf sea models is shown in the slide that you can't see, but if you look at it on the screens, you will see basically a map of the world with the continents, and around the continents a very thin stripe of color. That's the area where most of the catches take place. So most of the world's catches, fish catches, take place in a very narrow band around the continents. And that means that if you want to estimate potential changes, you need to have very good resolution models of the physical and biological processes in those shelf seas. And those shelf seas are driven by things like tides, like river outflow, like upwelling, things that global climate models do not capture at all well. So part of the work in this program was trying to develop these models. So what we did is in all the regions that you have in color here in this slide, in all these regions around the world, in those shelf regions, we developed these regional physical biological models. They covered 29 so-called large marine ecosystems. That's a governance sort of nomenclature. The models are 1/10 of a degree in resolution, so roughly about 6 square miles of resolution. Have 40 layers vertically to try to capture as well the dynamics there. Have daily resolution, so they run for every day. As I mentioned earlier on, it includes most of the important shelf processes, the tides, the upwelling, the recycling between benthic and pelagic domains, which is very important in shelf seas. And we did that by running these models for a pre-industrial time scale, roughly 1850, a present-day scenario, which is roughly around the 2000s, a near future in 2050, and a far future in 2100. Plus, we had a reanalysis simulation for the present day, so you can compare present day model results from a simulation reanalysis, as well as for the climate change model predictions. For each one of these scenarios, we ran the model for 13 years. The first 3 years was the model spinning itself, and the last 10 years was the actual data. And we used one particular climate change scenario, the so-called A1B, emission scenario from the French IPSL model. It is not that important. There are big differences between the different GCMs, but the important thing is to see what was the difference between the present scenario and the future in a particular model run. I'm going to go very quickly into the results, because I think it's important to move to the broader questions of the presentation, which is the socioeconomic consequences of that. What you have on the top panel, there's 2 panels there. The top one shows a difference in mid-layer depth temperature between 2050 and the present, and what you have basically is a lot of red and yellows, and that means warming. Any blues means cooling. So as we all know, global warming is expected to continue, and it's expected to be the case throughout the marine environment, but there are big differences. Some areas warm more than others. That's a very important consideration. Not every place warms at the same rate. The second panel on the bottom shows primary production change in percentage. So greens actually increases, red means decreases. And although it's very difficult to see at this sort of resolution, what is important to understand from this is that there are areas where primary production is expected to increase, and that is particularly in the northern latitudes, where primary production is constrained by temperature rather than by sunlight. And it is particularly expected to decrease towards the tropics, where certain processes such as coastal upwelling might be negatively affected. So again, the impacts differ from different places. Now, part of what the project was about is trying to also do some quality control of the estimates. And how do you do quality control of something that you estimate for the future? And the only way of doing that is by looking at the present run of the model and then compare with something that you have, for example, satellite estimations of primary production. So what you have in here is on one of the particular regions, this is the Indonesian domain, what you have is on the left panel is the principal component analysis, in other words, the variability of the seasonal signal of the primary production based on satellite information on the left, and on the right map, the same principal component analysis on the model primary production estimates. And what you see is two things. First, on the maps themselves, you tend to see a certain agreement between the blues and the reds. In other words, where the principal component is high and low, which means that geographically, the model tends to capture some of the variability that you observe from the satellite. That's a way of quality controlling your results. And in the panel at the bottom, what you see is a seasonality signal. That's the first principal component loading in time over the year from January to December. In blue is the satellite signal, and in red is the model runs. And what you see is that the model tends to capture the seasonality that we observe in the satellite. So again, it's an indirect way of perhaps validating that what we are doing, what the models are producing, makes some sense. Now, earlier on, John Pinniger, in an excellent presentation, has already described some of the problems of moving from what it is basically the basis of the food web, the phytoplankton production, the primary production, onto fish predictions. Because climate change will affect each one of these elements in a food web in a different way. And there will be additive components, there will be synergistic impacts, there will be antagonistic impacts. And it's extremely difficult to think how you're going to estimate those impacts going through the food web step by step. And in the past, there have been a number of approaches that have been followed. I'll just summarize some of them. One that has been followed quite successfully, particularly in Japan, but in many other places, is on the basis of individual-based modeling, getting a climate model, getting a dynamics of the ocean, and then putting a particular species' life history into it. This is Pacific sorry, and what these people did with this IBM is sort of mimic or simulate the migration of the species, and they say, if you hatch here, where would you go for your food? And if you then live for a couple of years, what will be your size, your weight, and so and so. And if you look at it in the future and a climate change scenario, how much further you have to go for your food, and as a result, how much faster or slower you're going to grow, and so and so. That's one of the approaches that have been followed to predict the impacts of climate change on fish and fish production. A second set of approaches are basically population models that use primary production and the distribution and abundance of primary production to drive the growth in the species and in the population. Patrick Lehodier and others have done this very successfully for example, this one for big-eyed tuna in the Pacific. They've also been, as John Pinniger mentioned, niche, or you can call it niche models or habitat models, where particular species are characterized according to their habitat, be that distance from shore, distance from the bottom, temperature, and on the basis of that, then look at the present and the future and see what the changes are. Very few approaches have actually taken the entire ecosystem. One of those approaches has been also mentioned by John early on, is this bioclimate envelope approach, where you classify every species according to their bioclimate preferences based on temperature, depth limits, and habitat. Then you run a population dynamic, you put it embedded in a climate model that determines changes in temperature and primary production, and that allows them to do things like, for example, in this paper by William Chong, potential change in catches between 2050 and the present, showing increasing catches in the northern latitudes, so in the high latitudes, and decreases towards the tropics and the central latitudes, based on bioclimate envelopes. As it has already been mentioned, and I was so happy that that was the case, those models have a number of problems, particularly that there are no ecological interactions included in them. So each species is parameterized individually and then combine the results. So in this project, what we try to do is find a way of simplifying this approach, cutting through this complexity of the food web and getting a system that would allow us to get fish production without all this complexity. And what we'd use is size-based modeling. Now, as everyone knows, ecosystems are fundamentally structured by size. You have a lot of very small things and a few very big ones. The size determines the metabolic rate of the species and therefore the consumption and production processes. Focusing on size means that you don't require to know the ecology of individual species and model that individual species ecology into your model. And as, again, we know, the production at the bottom of the web is fundamentally driven by climate. And there's a second important consideration, is that a number of papers in the recent literature and not so recent have actually shown that, in fact, the degree of primary productivity tends to be correlated to fish production. So, in other words, there is a link between primary production and climate. There's a link between primary production and fish. The difficulty is having the link between the one and the other in a way that is simple. So what we did in this project is two things. We used two types of size-based modeling approaches. The first one is called a static modeling approach, and it's been done, in fact, by Simon Jennings, who's here in the audience. And we also did a dynamic size-based modeling approach by Julia Blanchard, who's now at the University of Sheffield. Both of them are similar, but the dynamic model includes a time dependency and has continued growth and mortality in its algorithm. But basically what these models did, or particularly the dynamic size-based model, is that they used temperature, phytoplankton abundance, microzooplankton abundance, and detritus abundance from our models that I mentioned a moment ago, the physical biological models, and then output from that abundance through time at mass, so per size class, individually of the species. That's what ecologically that primary production can actually sustain. There's a number of parameterizations in there, which I won't get into at this point. What this allows as well is by applying particular fishing mortalities to those outputs, you can get potential catches at different fishing mortalities. And we use two in particular in this project, an F of 0.2 throughout the entire food web and one of 0.8 through the entire food web. So again, a bit of quality control on the results, on these results themselves. This is a complex figure, but it'll be easy to explain. What we did is we used existing data from the Sea Around Us project for the present landings for a period of 1992 to 2001, so 10 years of landings for 28 large marine ecosystems, get the average of those, and then compute what would be the equivalent landings using our model outputs for the same time periods. And then we divide them into EEZ, exclusive economic zones. So, and what you see in this panel on the left is the degree of deviation between the actual catches and the model predictions. Again, so that's for the present time. You're not yet predicting to the future. So what you have is for all this range of exclusive economic zones, if the dot is on the line, that means that there is no difference between the catch statistics and the model predictions. When the line veers towards the right, that means that the model overestimates, and if it goes to the left, model underestimates. And there are a number of reasons for that to be the case, but just in terms of getting confidence on the models, that shows that the model is actually capturing some of that variability. And we also did it by a domain, so we grouped them into big areas and then sort of related predicted catches with observed catches and see that the model, again, has some ability to capture what is happening out there. Summary of the results is that, on average, all these EEZ, on average, there's about a 2-degree change between now and 2050 in temperature, with a primary production change growth, an increase in primary production of about 14%, and a fish biomass change of about 3.4%. But the important thing is that it is very different from country to country. So many countries have a large increase in potential for fish production, and quite a few countries have a large decrease in potential for fish production. And that is what is most important, is to understand that all these global analyses and all these generic statements are probabilistic in many cases, and what matters is actually how they downscale down to the individual countries. Just a couple of the summaries of the points that I just mentioned. Fish productivity mirrored primary productivity. I didn't mention that. I'll mention it now. In fact, fish productivity followed more the changes in primary productivity than the changes in temperature per se. Okay, so it's not so much temperature alone, it's primary productivity in particular. But it is the combination between primary productivity change and temperature change that determine whether the yield is increasing or decreasing to a different degree. What this means effectively is that climate change is expected to change as well the susceptibility to overfishing, because it's a combination of whether you can have a warming but no primary production change, and therefore the impact to the food web will be different than if you have both warming and primary production increase. There are winners and there are losers, and that's something that a lot of people sort of forget to mention. The larger decreases in areas like Humboldt and the Canary Current, some of the upwelling areas. Some of this might not be perfect because upwelling processes are very difficult to model, even in high-resolution models, so there's an issue there. The larger increases are in the Nordic seas and particularly high latitudes. If anyone wants to know more about this actual part of the work of this project, there's a paper here recently accepted. Julia Blanchard is the first author in the Philosophical Transactions of the Royal Society. It's in press, so it'll be available very soon with the details of the modeling itself. The organizers asked me to particularly focus on the socioeconomic consequences, and as a matter of fact, I'm going to only partially focus on it. I'm going to give you almost the conclusion of it rather than give you to the whole detail. But basically what we did in terms of the socioeconomic consequences is that we used the predictions for fish production for each country and used it by separating how much of that fish would be used for human consumption, how much could be used for aquaculture through fish meal. We projected then to 2050. We looked at the human population needs by 2050 based on the existing food consumption patterns, and then we estimated whether it was possible to maintain the current fish consumption patterns in 2050 with a population much larger than we have now. As I said, I'm not going to give you all the detail. It's quite a complicated process, but I don't have the time to go through this. But the paper that summarizes all that work, or not summarizes, that explains what it is available here. Its first author is Gorka Marino from PML. It's in Global Environmental Change. It's already available, and it's entitled Impacts of Climate Change and Population Growth on the Sustainability of Global Fish Production. The main conclusion of this paper and of this work is that it is actually potentially possible to produce enough fish to maintain current global fish consumption rates in 2050, provided that the aquaculture efficiency rate is reduced from 0.7 to under 0.25. What does that mean? At the moment, aquaculture uses, for each kilogram of fish cultured, it needs 0.7 kilograms of fish as food. And that's the global aquaculture together. So if that's what brings the rate of 0.7, if that could be reduced to 0.2, then the expected fish production will be sufficient to feed the world at a rate of 19 kilograms per person per year in 2050, provided that we manage all the resources that we have according to maximum sustainable yield principles. So we maximize the yield across the food web, which is not an easy thing to do. But that is at least the potential. Another worker in this project, Mike Howling-Badger, published halfway through the project a paper that also looked at it from a different perspective, looked at the fisheries as livelihoods, and what are the impacts of climate change and climate variability on the livelihoods of fishery communities. And there are two main conclusions in that paper I think were worth bringing here. First one is that there is a need to recognize that climate change will actually bring opportunities to the sector in some areas. And that's something that many countries are already looking into. I can assure you that in Norway, for example, they are preparing themselves for climate change, and they don't see it as negative as other countries do. And so it's important that climate change will actually bring positives, and we have to bring that as well into the equation. And in places where fisheries really contributes to livelihoods, there is a recognition that fisheries has the potential contribution for mitigation of climate change, because climate change has impact on all the areas of food production, and in some places those communities can be sustained by fisheries when they have lost other ways of livelihood, and that's important to consider as well. As I mentioned, I wanted to just use last couple of slides to just almost prepare ourselves for the debate later on. And fisheries, there's been so much written on fisheries, whether there is no fisheries left, whether there's going to be collapsed by 2048. It is very difficult to know, really, the right state of fisheries at any given time. And there are very different ways of looking at it. I mean, the FAO, in the last report, it mentions that, 30% of the stocks are fished at full capacity. About 14 have not yet reached their full capacity. So that's 48% that are either fully fished or not fished yet. That means 50-something% are overexploited. It depends how you look at it, but it is actually not that straightforward. There was a paper recently in Nature where it equated the European fisheries to the production, 5 minutes, great, to the production of clothing and machines and I think that misses completely the point that fisheries actually is not just an issue of economic value, is an issue of livelihoods. Fisheries can be sustainable, they can be productive, and they must remain an important source of food, jobs, income, and livelihoods. I'll just put some flesh onto these concepts. First is an issue of equity. What you have on your left, I've put a number of maps that come in a paper by Eddie Allison in 2009 on fish and fisheries, and what it shows on the left is, in fact, the proportion of fishers. Where are fishers based? And what I've done on the right is actually just put them into a pie. Basically, this color that you can't see, that's fishers in Asia. That's in Africa, that's in North America, that's in Latin America, that's Europe. So when we look at the impacts of fisheries worldwide, we're looking basically at an issue of developing countries. It is an international issue of equity. Second, export value. The panel on the left is the value of fish exports for individual countries. And what you have on the right is the net exports of a number of food commodities for developing countries in billion US dollars. And fish contributes income to developing countries more than the export of any other food commodity put together. Put rice, put coffee, put meat, put bananas, put all that together, does not bring as much money as fishes brings to developing countries. And third, fish protein. Well, I just want to be a bit provocative, but this is meat production. In 2005, we produced just under 300 million tons of meat in the world. We produce 150 million tons of fish. So fishery is about half of the meat production. It's a big part of protein production in the world, isn't it? And when we look at sort of meats, this production, this 300 million tons of meat, requires over 1,000 tons of feed to produce. The human consumption of meat currently is about 40 kilograms per year. It was about 30 kilograms per year in 1980, so it's grown considerably over the last 20 years or so. The human consumption of fish is about 19 kilograms per year. It was about 10 kilograms in 1960, so it's grown, but not as much. There is an issue about our protein consumption. It is an issue, and that really is what, to me, needs to be looked at. And I find it quite surprising that there's so much debate about these 150 million tons that are produced as fish, and yet so little debate about the 300 million tons that we produce as meat. I mean, some of you have actually landed on airports in the last couple of days, and when you land in the UK, the first thing you see is actually this beautifully partitioned land for agriculture production, and no one finds that at all surprising or upsetting. They love it. It's beautiful. It's all green. But actually, none of it is natural. And yet, when it comes to this 150 million tons of fish, we all tear our hairs. But I think there is an issue of balance that needs to be put into the picture. Just finalize quickly. I'll pass that. There was a paper by Simon Levine recently called Crossing Scales, Crossing Disciplines, Collective Motion and Collective Action in the Global Commons. 1 minute. What he mentions there is that basically that in the discussion about evolution, people tend to focus very much on the survival of the fittest and the individual success, but there is actually a principle in evolution which is about collective behavior, and multicellular organisms is actually the greatest example. And what he mentions in here is that, in fact, we have to understand the basis of cooperation and take multicellularity at a higher level. And what do I mean by that? Is that individually we feel that we bear not the full cost nor the full benefits of the common goods, and that we feel only marginally responsible for the problems that we have in the common goods. So we need to have an issue, resolve the issue of ownership. Who owns the resources? It's important to determine that. Second, we feel as well that our individual efforts will do little to improve the future because it's just our individual efforts. And then we'll have to take into account the fact that, as we mentioned today, there's an issue of multiple uses, multiple impacts, and multiple objectives that we need to take into account. And finally, reciprocal altruism does not work in a globalized world. So if you share a field, you can actually think about being altruistic and expect some reciprocation, but you can't do that in a globalized world. So for that, we need to depoliticize management. And by depoliticizing, in my view, means, in fact, removing the management from the individual politicians of individual countries. Bring it to a global political arena where you can make the big decisions and bring to the stakeholders and effectively the owners of the resources once they are defined to get into the application of the rules. The moment that if we stuck onto the politicians of the individual countries, it's extremely difficult to push forward an agenda that will actually sustain our resources in the future. Thank you.